Hi, welcome back. In this video I will discuss how to generate object code and object program for a given SICXE program. This is the solved example number 1. The link for other example is given in the description below. In this case we have been given a program. Along with that, for each of these opcode we have been given the mnemonic codes also. So given this thing, we need to first calculate the object code and then we need to generate the object program in this case. So first we will try to calculate the location counter for each and every instruction, and then we will get the object code. Finally we will try to convert this object code into object program. In SICXE we have 4 type of instructions: type 1, type 2, type 3 and type 4. Whenever we have a type 1 instruction, it will be of size 1 byte, type 2 2 bytes, type 3 3 bytes, type 4 4 bytes in this case. Now I will start with the first instruction. The first instruction's location counter is 0 because the operand value of this particular program is set to 0 here. So this is 0 in this case. Now if you look at this particular instruction, this instruction is of type 2 because this instruction has the registered involved in it. If there is a register, it is type 2 instruction. That is the one thing we need to remember. Now what we do here is the initial value in this case is 0. To this particular 0 we will add 2 to this one. You will get the next location counter here. So the location counter for this instruction is 2 in this case. Now if you see this instruction is type 3 because there is no register. If there is a register, it is type 2, and if there is a plus, it will be type 4 in that case. Because there is no register, there is no plus, this instruction will be type 3. If it is type 3, we need to add 3 to this one. So if I add 3 to this particular thing, I will get 5 here. So that is what I have written. And this particular instruction is of type 4 because plus is there. So I will add 4 to this one. I will get the next one as 9 in this case. Now this one is the assembly directive. I should not write the location counter for this particular base here. Now if you look at this instruction, this instruction does not have a register here, and there is no plus, means it's a type 3. I need to add 3 to this one. I will get C here. Now this instruction is of type again type 3, so I will add plus 3 to this one. I will get F for the next instruction. This instruction is again type 3. I will add plus 3 to this one. I will get 1 2 in this case. Again this is type 3. I will add plus 3 to this one. I will get 1 5 in this case. This instruction is again type 3. I will add 3 to this particular thing. I will get 1 8 in this case. In this case we are reserving some words. How many words we are reserving? That is one word we are reserving. One word is equivalent to 3 bytes. I will add this to this the previous address. I will get 1B as the location counter for this instruction. In this instruction we are reserving 2000 words. 2000 words is equivalent to 6000 bytes. So 6000 bytes should be converted into hexadecimal number first, that is 1770 what we can say that the bytes here in terms of hexadecimal, and then we need to add this particular thing to the previous one, that is 1B. Once you add it to this particular 1B, you will get 178B as the location counter for the next instruction. This instruction we are reserving only one word. One word is equivalent to 3 bytes, so I will add that 3 bytes. I will get 178E as the location counter for the last instruction in this case. So this is the procedure we need to follow to get the location counter. Now we will try to find out the object code for each and every instruction. Again we follow this particular the types, whether it's a type 1, type 2, type 3 or type 4. Based on this particular type of instruction and the type of addressing mode, we will try to come up with the object code here. Now we will start with the first instruction, that is clear X. The clear's mnemonic code is B4, and then one more very important thing is clear is of type 2. Its instruction format is first 8 bits are opcode, next one is register, next 4 bits, next 4 bits for next register in this case. So B4 will come and sit at the opcode position. The value of this X, or the mnemonic value of X, is equivalent to 1, so R1 is equivalent to 1, R2 is not present, so it is 0. So it is B410 is the object code for this one. Now coming back to the next one, it's a type 3 instruction. Because it's a type 3 instruction format is something like this. First 6 bits are opcode, NIXBPE. N means indirect addressing mode, I is immediate addressing mode, X is index addressing mode, B is base relative addressing mode, P is a program counter relative addressing mode, E is set to 0 if it is type 3, E is equivalent to 1 if it is type 4, 12-bit displacement is used if it is type 3, 20-bit address is used if it is type 4 in this case. Because it is type 3, and if you look at this one, hash means it is a immediate addressing mode. So I will be set to 0 and N will be set to 0, X will be set to 0 in this case, base will be set to 0, P will be set to 0. Only I will be set to 1, remaining all will be 0 here. E is set to 0 because it is a type 3 in this case. And 12-bit displacement will be equal to 0 in this case because we don't have any displacement when it is a immediate addressing mode. That too in type 3. Now what about the type opcode? Opcode is 6 bits opcode we have to take. So I will go to this particular LDA. LDA value is 00. So 8-bit 00 is represented something like this. We will take the most significant 6 bits here. We will write it here. Now the first 4 bits are 0. Next 4 bits are 0001. Remaining is 0 here, and these 12 bits are zeros. So the meaning is 0 1 0 0 0 0 here. So that is what the object code we will get here. Now coming back to the next instruction, the next instruction is LDB, and it is a type 4 instruction. In type 4 we will get 20-bit address here, not the displacement. That's the first thing. Because of that, this is the type 4, we will set E is equivalent to 1. And if you look at here, it is an immediate addressing mode. So I will be set to 1, remaining NXBP will be set to 0 here. Now coming back to this opcode, the mnemonic code for LDB is equivalent to 68. So its binary representation is this one. We have to take the most significant 6 bits here. So I have written the most significant 6 bits here. Now we will try to convert entire thing into hexadecimal code. So first 4 bits are 0 1 1 0, that is 6. Next is 1001, that is 9, 0001, that is 1, remaining is 0178B, that is 6910178B. That is what the object code for this instruction. For base, we don't have any object code. We will come to this one, that is add table comma X. Now when it comes to this one, very first thing we need to see here is adds mnemonic code is how much? 18. So the representation is written here. The most significant 6 bits are these 6. These are the most significant 6 bits. I have written it here. Now if you look at this particular instruction carefully, we have comma X. Comma X is nothing but what? Indexed addressing mode. So it is neither immediate nor indirect addressing mode, but it is a indexed addressing mode. Neither immediate nor indirect. It will be set to 1 1 here. Index addressing mode, that's the reason it is set to 1 here. And then we have to calculate whether it is a base relative or program counter relative. That's one more thing we have to decide. So we have to decide this particular thing by the value of displacement here. We will do this particular thing at the later stage. And E is equivalent to 0 because it is a third type of addressing mode in this case. Third type of instruction in this case. Now displacement, how to calculate the displacement is the value of table is equivalent to 001B, that is what I have written, minus the PC value, the program counter relative addressing mode we will try to check. So the PC value in this case is 000C, 000C. If I calculate this particular equation, we will get F here. This F is present in this range, that is minus 2048 to 2047. Because it is present in this range, we assume that the given instruction is program counter relative addressing mode, not the base relative addressing mode. So P will be set to 1, B will be set to 0 here. Now what is the displacement we got? F here. So we need 12 bits of displacement. So we will write 00F. 0 is 4 bits, this 0 is 4 bit, F is 4 bits here. Now entire thing will be converted into hexadecimal code, that is 1 here till here 1, 1011, that is I think B, and then we have this one, that is 1010, that is A, 00F. That is what I have written in this case. Now coming back to the next instruction, that is TIX count. So TIX, its mnemonic code is equivalent to 2C. Its binary representation is this one. So this is the most significant 6 bits. I have written it here. Now if you look at this particular thing, there is no hash, there is no @ symbol. The meaning is it is neither immediate nor indirect addressing mode, so we will put 1 1 here. There is no comma x, so we will put 0 for x. Now we have to decide whether it's a program counter or base relative. We will do it later. E is set to 0 because it's a third addressing mode, third instruction type, and this displacement we have to calculate. Based on that we will decide whether it is base relative or program counter relative addressing mode. Now displacement is always equivalent to the value of this particular count. What is the value of count? 0018, and the program counter value at this particular location is, the program counter always holds the address of the next instruction, that is 000f. So 0018 minus 000f, which is equivalent to 9. So 9 falls in this particular range, so it is a program counter relative addressing mode. That is p is equivalent to 1 here and b is set to 0 here, and this 9 is represented as 009 because we need 12 bits here. Now if you convert entire thing into what is that called as the hexadecimal number, we will get 2 for this one, 1111 that is f, 0010 that is 2, 009 here. That is what we got in this case. Now coming back to the next instruction, that is JLT. JLT's numeric code is equal to 38. Its representation here is here. Now get the most significant 6 bits, write it in the opcode field. Because we don't have anything called as hash and @ it is neither immediate nor indirect addressing mode, 1 1. There is no comma x, so it will be equivalent to 0 here. Now we have to decide whether it's a program counter or base relative. Again we will do it later. E is equivalent to 0 because in this case we don't have anything called as plus here. Now how to calculate the displacement? Displacement is equivalent to the value of loop, that is 0009 minus program counter value. The next instruction's address is 0012. So 9 minus 12 is not possible to calculate. So 12 is in hexadecimal. That's a very important thing. 12 hexadecimal representation. Hexadecimal 12 minus 9 is equivalent to minus 9 here. Because this minus 9 falls in this range, p is equivalent to 1 and v is equivalent to 0 here. Okay, and now this minus 9 we cannot write in the displacement. So what we do, we will convert this thing into 2's complement form. So if you calculate the 2's complement form of 9 here, you will get ff7. So that is ff7 is the displacement in this case. Now again convert entire thing into hexadecimal code by clubbing 4 bits. You will get this particular number here. We will go to the next one, that is STA total here. STA's number is 0C. This is the representation. Most significant 6 bits are represented here. Now it is neither immediate nor indirect again, so 1 1 here. There is no comma x, so x is equivalent to 0. We don't know whether it is program counter or base relative. We will do it later. E is equivalent to 0 at this particular point of time. Now we will try to calculate the displacement to see whether it is a program counter or base relative addressing mode. So the displacement is the value of this particular total, that is 178b, I have written here, minus the next address that is 0015, whose value is equivalent to 1776. 1776, if we convert this particular thing into binary, or you can say decimal number, it will not fall in this particular range. The very simple reason, we can have only 12-bit displacement. If you look at here, it's a 16-bit displacement we are getting here. So definitely it will not fall in this particular range here. Again, I'll tell you, it is a hexadecimal number. So if you convert into decimal, it will not fall into this particular range. That's the one thing you can see. Or else, if you see here, there are 16 bits are there, 4 bits for each, but we have only 12-bit displacement. So definitely it is not a program counter. So it should be base relative. So base relative addressing mode, B will be set to 1, P will be set to 0 here. E is 0 because it's a third type of instruction here. Because it's a base relative addressing mode, again we have to calculate the displacement. That's a value of this particular total is definitely 178p minus the value of base register. What is the value of base register? In the base register we are storing the value of total again. So what is the total value? 178p. 178b minus 178b is equivalent to 0 here. So the 12-bit displacement is 0 0 0, that is 12 bits are there. 4 bits for this, 4 bits for this, 4 bits for this one. So club 4 bits, you will get the value is 0f4000 in this case. That is 0 till here. 1111, that is F, 0100, that is 4, and these are 000 here. Now coming back to the next instruction, that is rsub. Rsub is a type 3 instruction. The mnemonic code for rsub is equivalent to 4C. The most significant 6 bits are over here. It does not have anything called as a register here, no address, nothing is there. It's neither immediate nor indirect addressing mode, no index addressing mode, no base relative, no program counter relative addressing mode here. And it is what we can say that type 3, so we will set it to 0 here. Because nothing is there, we don't calculate the displacement also. Displacement is also 0 in this case. And if you convert this thing into hexadecimal number, the first 4 bits will give you 4, next 4 bit will give you F, remaining everything is 00 here. So it is 4F0000 in this case. Now coming back to the next instruction, this is a reserved word, so we don't calculate object code for this one. The next one is again reserved word, we don't calculate object code for this one. For this one also we don't calculate it. End is again, it's a assembly directive, we don't calculate the object code here. But for this one we will write the starting address. The starting address in this case is 0000 over here. Now we got the object code for each and every instruction. We will try to convert this object code into object program here. The object program contains 3 sections. One is called as a header section, text section, and then the end section. The head section starts with the H, followed by 6 columns for the name of the program. What is the name of the program here? SUM. We will write SUM. 3 columns we will leave blank here. After that we have to assign, we have to write the starting address of this particular program in 6 columns. So that is 0000 we have written, but we have 6 columns, so we will add 00 to this particular thing. The next 4 columns will represent the length of this particular program. The length is the starting address of the last instruction minus this particular thing. That is 178E minus 0000, which is equivalent to 178E. That is what I have written here. Now coming back to the text section, it will start with the T. After T, we have to write the starting address of this particular text section, because you may be having multiple number of text sections. Out of that, this particular text section starts from 000000. That is the in 6 columns we have to write here. So text section starts from here. Again, let us say that if the next text section starts from here, it will be 00000F. That is the starting address. I will tell you about this 18, how to write it later. After this particular thing, we have to write the object codes here. Now, how many object codes we need to write is the totally 69 columns will be there in each and every text record. Out of that, 1 column will go here, 6 columns over here, that is 7 column, 2 columns for this one, that is the length of that particular text record. So totally 9 columns were gone. Remaining 60 columns you can write the object code here. If it doesn't fit in the one text record, you can write the one more text record over here. So you'll go on writing the text records. That is the first one I have written here, second one, third one. All the text records I have written in one text record, because if we count here, this is 4 columns are there, 6 columns, that is 10, 11, 12, 13, 14, 15, 16, 17, 18 columns here. 18 plus 6 is 24, 24 plus 6 is 30, 34 plus 6 is equivalent to 36, 36 plus 6 is equivalent to 42, 42 plus 6 is equivalent to 48. So totally 48 columns are there for this particular object code. Now this particular 48 columns are there. 2 columns is equivalent to 1 byte. The meaning of this one is 48 columns, which is equivalent to 24 bytes in this case. 24 bytes, because 2 columns is equivalent to 1 byte, 48 columns is equivalent to 24 bytes. Now we have to calculate the 24. This 24 is a decimal number. Its hexadecimal representation is equivalent to 18. I hope you can see here. The decimal representation is 24 bytes and its hexadecimal number is equivalent to 18 here. So that is the reason I have written 18 as the length of this particular text record. So length is represented in the form of hexadecimal value here. So this is the text record, because everything is written here, so we will stop here. This is not an object code, this is starting address. So that's the reason we don't consider this one. Now coming back to the end record starts with E, and then we have to write the starting address of this particular program. The starting address of this particular program is equivalent to 000000 in this case. So that is the last thing over here. So this is how the final object program looks like for this particular given SICXE program in this case. So in this video I have discussed, given an SICXE program, how to calculate the location counter, how to calculate the object code, and how to convert this particular object code into object program over here. This is the solved example number 1. The link for other example is given in the description below. I hope the concept is clear. If you like the video, do like and share with your friends. Press the subscribe button for more videos. Press the bell icon for regular updates. Thank you for watching.